They're more amazing than you know.
I'm sure.
Rocks along here, Randy.
Rocks. When I was
Rocks.
you know, high school and the visible trees.
Here, because this is a piece of granite that came in much later than most of the geology here. In this particular area, I described the fault at the last stop. You know, I talked about the myelinite created by the grinding along the fault. That fault was then folded into a hairpin, which is quite severe. That hairpin was refolded again. And after all that happened, after all the folding, after all the faulting and all the folding, then the granite here was put in. How do we know the granite came later? Anyone remember how you tell whether something came earlier or later? There's a couple of criteria. Cross-cutting relations.
You don't even need radiation.
Cross-cutting, and you can see here is the layering of the myelinite here. It comes up and ends against the granite. Therefore, the granite came in after the deformation. The granite, you can't really see it here. I take other people's word for this. The granite does not show any of the folding and deformation. The fault itself is tightly folded. So that means that the granite post-dates not only the rock itself, but all the deformation that the rock has undergone. Once it's explained, it seems reasonably obvious. So then the question is, when did the granite come in? So we can get some idea of how old the rock is. It's a very poor idea because all it does is put a boundary. The rock can't be any younger than the date of the granite. How much older? That we're not quite. We do have a way of getting to that, but not very well. Anyway, it turns out this granite has zircons in it. And as you know, zircon is a very, very good mineral. It is the best mineral for radiometric dating. The zircons have a little tiny bit of uranium in them. The uranium breaks down to lead, and if we measure the amount of uranium and the amount of lead, we can stick it in that little equation I gave you and come up with a number. And the number here is 475 million. Now that's an interesting number because it turns out the Appalachian Mountains started going up around that age. That's the first phase of the closing of the old Atlantic Ocean, and that's when the granite came in. So that means all the other deformation we have here came before that. And that really is a problem because it turns out this was at the edge of North America at the time, and North America before 475 million years ago, this edge was very much like the edge of North America today. Nothing is happening geologically. It's coastal plain. You're getting the deposition of sand and mud and clay, and all it's doing is just sitting there until the ocean starts closing at 475 million. When we get out a little bit west of here to Sugarloaf Mountain, we'll see rocks of just the same age, and those rocks were deposited on a quiet continental edge with nothing happening. That's 30 miles away. Here, all hell was breaking loose geologically. There, nothing. It turns out that the old Atlantic Ocean, called the Iapetus Ocean, was closing at the time, but it was closing over on the other side. There was a subduction zone going on over on the African side of the ocean, and as I say, all hell was breaking loose geologically with volcanoes and thrust faults, really, really badly messed up. Okay, now we got these rocks here. Which side of the ocean was it on? Well, judging by the fact that all hell was breaking loose here, it's African. That's the reasoning. So these are African rocks, or at least on the other side of the ocean. We can't say for sure that it was part of the continent of Africa, but it was over on the other side of the ocean. It might have been an island on the east side of the ocean. African mainland, can't say, we don't have the information on that. Okay, is that fairly clear?
But how did they wait? How did they
Yes,
get
of
here?
course.
Didn't you say like when the continents had split it, like they left like a landmass in between before you got here?
Well,
to
when the
the-
continents, actually in this particular area, in this area of Maryland, there have been two separate supercontinents, both of which split apart. If you go back, actually it's my other field trip that takes us out to the Blue Ridge. There you see the evidence of the assembly of a supercontinent, Rodinia, about 1.1 billion years ago. It then broke apart 750 plus or minus million years ago, opening up a brand new ocean called the Iapetus Ocean, which I'm now calling the Old Atlantic. And it kept getting wider and wider until about 600 million years ago, when it started closing again. And it started closing on the other side of the ocean. About 475 million years ago, it started closing on this side too. That's where that igneous rock comes from. And then about 250 million years ago, the ocean was wiped out of existence and we assembled a second supercontinent. That's the one most people have heard of, called Pangaea. Okay, and so we had Pangaea at 250 million. Then about 180 million years ago, that supercontinent split apart, opening up the modern Atlantic, which is still opening up today. If you want to see it, you can go to Iceland, because there, the crack that runs down the middle of the ocean comes up on land, and you can actually climb down into the crack, because it's still cracking open today.
I have.
If you wait, I don't know how long, that crack is going to fill up with lava, and it won't be a crack anymore. It'll be solid rock, but it'll keep pulling apart, and it'll open up again.
So Dennis, there've been volcanic activity in Iceland recently. Is that part of that crack? That volcanic
It's
activity?
part of the same. It's part of the same thing. Actually, there's not just one crack. I'm
Right.
oversimplifying. I always do. And it turns out there's a whole set of cracks.
Okay.
And the same was true when Pangaea opened up originally. As a matter of fact, one of those cracks is now the Atlantic Ocean. Another one is the area around Seneca. And we're going to see that the result of that particular crack. It's a place where the continental crust pulled apart. A block dropped down like a keystone in an arch if you pull the two sides of the arch apart. The central stone, the keystone, will drop down, and then it fills in with sediment washing in from each side. We're going to get to see that sediment just before we have lunch.
That'll be the red stone, right?
That's the red dinosaur age stone. Okay, any other questions on this particular rock here? This is the only place we'll see the granite, which is why I stopped here.
Dennis, explain this big hunk of quartz here.
Oh, the quartz.
huge
The
piece of
quartz
quartz.
is something else again. This is actually a quartz vein running through here. It's almost pure quartz. Rosa's little pet rock came from a vein like this. It's very resistant. And it wears down to nice, smooth, round stones like that. Now, quartz has a melting point that is extremely high. It's about 1,700 degrees Celsius, which is close to 3,000 degrees Fahrenheit. Rocks don't get that hot. And what happens here is, at temperatures like 400 or 500 degrees Celsius, the quartz will dissolve in high-pressure hot water, what's called a hydrothermal system. So this is rock that was deposited by extremely hot water. As it came through the rock here, it cooled down, and as it cooled down, it deposited quartz along the way. So it's very common in low-grade, that is slightly cooked, metamorphic rocks. 300, 400, 500 degrees, that's not really high grade in metamorphic rocks. You don't need to melt the quartz. to get it coming in like that.
So no garnets here.
There are no garnets here. This is a little bit too low grade for garnets. Now, one other point, the Mather Gorge Formation itself here does contain zircons. But those zircons are what are called detrital zircons. They were part of the original sediment that was deposited to make the formation. It predates the rock itself.
What's that
Zircon
word?
is like quartz, except even more so. It's harder and more resistant than zircon. Once you make a zircon crystal, it goes on almost forever. Almost nothing can happen to it. Wears away slightly, it can get rounded a little bit, but that's about it. Now, if you get the dates on the zircon here, that tells you not the date of the rock, but the date of the original igneous rock, which was broken down by weathering and erosion and transportation before it was redeposited in the Mather Gorge Formation. And if you measure the zircons here, you'll find there's a whole range of ages, which go back to maybe almost 1.5 billion years, 1.3 billion, down to 1.1 billion or even more recent, because it came from a variety of sources. There's not just one age at all. It's the age of all the rocks which were eroded away to give you the sediment. So that does put an older bound on how old this rock is, because the Mather Gorge has to be younger than the youngest age you get from the zircons. And the Mather Gorge has to be older than the age of the zircon and the granite that cuts through it. Unfortunately, that leaves a very large range of time possible for the Mather Gorge. We think we know that the Mather Gorge is somewhere around 500 to 600 million years old. Might possibly be 700 million. But that's a best guess. One of the things I try to do is explain to students, when you read about something like ages of rocks or what happened at a given time, a very good question to ask is, what's the evidence for that? How do you know that? Sometimes the evidence is really good. Sometimes the evidence is well, as I think it was Mark Twain said, something like finding a fish in your milk. It's evidence that there was something nasty going on, and pretty good. Other times, it's a pretty well-educated guess. Other times, it's sheer guess. It's what we think, and can you prove me wrong? And it's sometimes useful to know which this is. If you go back, 100 years ago in geology, almost everything was, it's just a guess, because we didn't have any numbers at all for dates. There were no dates given at all.
No radioactivity.
There was no radiometric dating, because although 100 years ago they did have radioactivity, they did understand it to some extent. They hadn't begun to use it for dates yet. Okay, let's go down and look at some fresh Mather Gorge that hasn't been faulted. It's not all ground up, just down the road here.